every member of A also is a member of B. It will be a proper subset if every member of A is or a member of B also, but they two are not equal. Okay. So after that, we have seen many other terms like multi-set. What is multi-set? And union, intersection, complement, Venn diagram, uh, set of natural numbers, integers, empty set, singleton set, unordered pair. So what was unordered pair? Can anyone tell me what is unordered pair?
Yes, ma'am.
Ma'am, when elements are
A
not follow
set
the
of
order.
yes, ma'am. If the pair don't follow any sequence, then it will be unordered pair.
Actually, a set with two members is known as unordered pair because we have not talked about sequence till then. So unordered pair is just a set of two members. Like singleton set is a set of one member only. Like that, unordered pair is a set of two members. What is power set? Power set is a set that contains all the subsets of a set. Cartesian product is the cross product of two sets, and their example is given here. Sequence. Now there comes sequence. Sequence for any set is all where all the members of the set will be there, but they are going to be following some order. Where all the members of the set will be there, but they are going to follow some order. And one sequence is not same as the other sequence because with all the members of the same set with a different order, the two sequences are not same. And in a sequence, they are represented using only first bracket. There is no second bracket. Now, the thing is, what I wanted to say is a sequence of two members. A sequence of two members is known as ordered pair. A sequence of two members is known as ordered pair. The reason I am telling here it is because we have just said what is unordered pair. Now our next question that came up is what is unordered pair. So ordered pair is a sequence of numbers in a set. Two members will be there in a sequence where two members, that is known as ordered pair. We have seen Venn diagram and we have created some Venn diagram. So this type of questions can be there in the exam. After that, we have learned what is function. A function is an object that sets up an input-output relationship. Function is an object that sets up an input-output relationship like we can see here. And we can also say that function maps. The task function does is also called mapping. And what it does and how we can say that? We can say that f is a function which maps the value of a to b, the value of b. Function f maps a to b. There is one important topic now. What is domain and what is range? So the range. Domain are the inputs. Domain are the all possible inputs for a function, and range is the all possible outputs for a function. Now, domain means what are the possible inputs for a function. Now, there is one more thing. Domain with k arguments is known as k-array function. What is this k argument? K argument means there are k possible types of input. In the domain, k arguments means there are k possible inputs, k possible formats of inputs, not k inputs. So it is known as k-array function. K is known as arithmetic. When in the domain there is only one possible input, it is known as unary function. When in the domain there are two possible arguments for the input, it is known as binary function. An example of unary function is given here. An example of unary function is given here. The function says absolute value of a, and the input is all real numbers. Input is all real numbers. In the absolute function, we are taking input all real numbers or all integers, and integers uh, range start from minus infinity to plus infinity. And if we take any minus number or any positive number, they are going to give us only the positive numbers output for the absolute function. Now, as we have seen, as we have said, that there will be one possible argument as input. Now, here the possible argument is z, which is representing all the integers. Okay. Now we can see we have another function that says add a comma b. It means that you have to add the values of a and b. And we said that for a and b, the inputs are the two real numbers. Inputs are two real numbers. So the domain is according to the domain, because there are two numbers. It is binary function, and we have two arguments, two z. So these are going to be represented using the cross sign, not the multiplication start sign. They are going to be represented using the cross sign. Now, it says that if the function is a binary function, they are better represented using the infix notation. And what is this infix notation? It looks like this, where the operator is placed between the operands. Operator is placed between the operands. It is known as infix notation. It uh, it it is better, or it is suggested that we don't use the prefix notation. And what is prefix notation? The one we use normally, where we place the name of the operation in the first place, and then we place the operators in the second one. That is known as prefix notation. So in case of binary operation, it is used, infix notation is used. So it took me a long time for giving you a review of the previous class, but that was all we have learned in the last class. Okay, we have some more
Yes.
things left for the function part. For the function part, we have more things left. So what are the things that we are left with? We have predicate. We have predicate. So this is the new thing for today. And what is this predicate is? What is this predicate is? Predicate or property is a function whose range is true or false. Predicate, it also has a name, that is property. Predicate, or we can say it is also known as property. So predicate and property is a function which range is true or false only. That means you can give anything input. The domain can be varied. It can have different types of input, but the output will only be true or false. For predicate, it's a function where the output is going to be only true or false. Okay, so there is an example given. While I am going to discuss the example, before that, I want to say something, and it is that you can see that it is proving some function for predicate. The example given here, it is proving some function for predicate. Okay, now how we can prove this function? The way we can prove this function, there are two ways for proving any function. or describing any function, we have two ways. One is we just can perform the calculation that we have in the function. Maybe we have different types of function. We know that we have different types of function. Like if I say that it can also be considered as, so we can represent this as, we can represent this as this. So how we can describe this function? We can describe this function like for x, we know that x is going to be z. That is any type of number. We can prove it for any different types of number, like a for 1 plus 45. We can say this. So x y is 46. We can prove it like this. Or what we can do is we can create tables, or we can say this is we can call tables. We can create tables for possible input and output. This can be one dimension. For this one, it will be one dimensional table. And for the example, you can see here, it is a two-dimensional table. So we can describe any function using either calculating the values of the function, or we just can use a table for the value calculation. Okay. So we can describe any function either using the calculation process or just using the table that we have here for any type of function. Now the thing is, the example given here is an example for predicate, where you can see the output is, these are the outputs. This is the input, scissors, paper and stone. These are the input and the outputs are placed inside the table. Outputs are placed inside the table. Now what is happening here? Let me tell you the thing, what is the function and what is happening here. So the function name here is bits. Function name here is bits. And we can say in the first one is A, and the function maps to B. Okay, so A holds the value is scissors, paper and stone. For B, we can write that it is true, or can be true, or it can be false, because this is the range of values for any predicate. Okay, so we can see bits. Bits, it will be two, the function is not defined yet. There will be two things. Why there is two? Because we can say A and A, because we have to prove that this is between this one. So we have to compare two values. That's why I have written here two. It is a function that happens between two inputs. Okay, and the range is scissors, paper, and stone. Scissors, paper, and stone. It is basically the rock, paper, scissors that we have seen. So it is an implementation of those. So the first one, this the line, the column is considered as the first value, and then the scissor, then the row. How is that? It says scissors beats scissors, or paper beats scissors, or stone beats scissors. So if it is possible that according to the rule of the game, the output is placed. Like scissors beat scissors. Is there any output? No, there is no output. That's why the result is false. Paper beats scissors. No, paper doesn't beat scissors. That's why the output is false. But stone beats scissors. It is true. After that, we have scissors beat paper. It is true. Paper beats paper? No. Stone beats paper? No. So this is false. Again, scissors beats stone? False. Paper beats stone? True. And stone beats stone? False. So their relationship of the function is represented using this table. So we have used this table to describe the function, and the example is given here, that how to represent the function, or you can have a detailed description of this. For the example, you will find many other examples for this later.
Ma'am, is there any rule that if one is true, the rest of the is false?
I did not understand. It will be one is true, another will be false. It is not like particularly for any operation. It based on the function actually, that what will be the output. It will be based on the function. Like the function is bits here. It will be like any other operation could be there, which will have true or false. And for those operations, it is not actually confirmed. You say that one is true and others is false. This is also possible, but based on the function only. Okay, so it is also possible if the function supports this, but this function only supports that one will be true and the other will be false. That's why this function doesn't support it. It supports an output like this, where there is three outcomes. One can be true, and in each case there will be one true and other false. Okay, that is related to each part of that. So it is not fixed, but according to the function, the output will be there. Okay. Now there is one more thing, as we discussed in the previous part, that the arity that we have discussed based on the domain of this thing, domain of a function. Now for any predicate, the arity, based on the arity, the number of inputs of a function, it is number of input arguments in a domain. It is known as k-array relation. Okay, if there are k arguments in the predicate function, so it is known as k-array relation. Look this thing carefully. It is not k-array function. It is known as k-array relation. So we have three inputs here: scissors, paper, and stone. So it is known as three-array relation. So it is known as three-array relation. So same thing, but it is not going to be called function. It is known as relation. Okay, it is known as relation. So it is not called function. The arity of predicate function is known as k-array relation. Okay. So there are many other functions now involved, many other relationship of this predicate thing you can say. There are many other relations. Okay, so these are some special kind of relations. These are known as equivalence relation. What is equivalence relation? This relation captures the notion of two objects being equal in some feature. It finds out that if two functions are equal in some feature, a binary relation R is an equivalence relation. So a binary relation R will be an equivalence relation if it satisfies these three things mentioned below. A binary relation. And what is binary relation? We already know what is binary relation. We are considering, say, R is the relation between two things, between two values, between two arguments. R will be a binary relation. R will be equivalence relation. Equivalence means that it will be capturing the equality of two functions in some features. So a binary relation will be equivalence relation if it if it satisfies the following thing. So what is this satisfying? That for every x, it will be the relationship between x and r will be equal. It will be, these two are going to be equal because we said r is satisfying the relation of equity. It is satisfying the relation of equality. So for every argument in x, if x is going to be equal to x. Now we call it symmetric if there is an y, and if we place them one side or other side, it implies the same thing. The relationship, that means if I say that r, if we take it as equal sign, x is equal to x and x equal to I, y is same as y equal to x. Okay. Transitive is another relationship. We have seen this thing. If x is equal to y and y is equal to z, that means x is equal to z. So R will represent an equivalence relationship of equality if if it satisfies the following condition, where we can see that x is going to be equal to x and x is going to be equal to I, and it will be implying the same thing as you can see here. Okay, so is there any confusion related to these things?
Yes, ma'am.
Yes, tell me what is the confusion.
Ma'am, what is this, ma'am? K-array relation. It is the we assume the K-array relation, or ma'am, there is a
Have not assumed. I assume that you understood the k-array function part. I assume that you understood this part.
okay, ma'am.
So did you understand this thing?
Yes, ma'am.
So that means there will be k arguments, k amount of inputs in the function. So that defines the arity of the function. But in case of predicate function, this k array function is known as k array relation. It is not it is not known as function, it is known as relation. Okay. So it is the difference between the normal function and predicate function, that it is known as k-array function and it's known as k-array relation. Okay. Okay. Any other confusion related to this thing? Any other
ম্যাম,
confusion?
তাহলে কে এর ভ্যালু হচ্ছে নাম্বার অফ ইনপুটস।
Number, actually you cannot say number of inputs, you can say number of arguments taken as input, because as we discussed in the previous class also, that we said that z is representing all the integers, and inside the integers, do we have any definite number of numbers? No. Number of inputs? No. We can take the inputs from minus infinity to plus infinity, isn't it? Minus infinity to plus infinity is the thing we can take. So it is encompassing a variety of numbers. So we call them the inputs. We call them is what I don't remember. Inputs we call them arguments. So the number of arguments, based on them we create this relation. The number of arguments, based on them we create this relation. Okay. Any other? Any other confusion?
No, ma'am.
Okay, then let's take your attendance. us the remainder value. So we want to prove that modulus is a relationship that is an equivalence relation. That is an equivalence relation. And how can we prove this equivalence relation? We can prove this, and this is an equivalence relation if we have we are proving these three things. If we are proving these three things, that then we can say that we can say that we can say that the two relations are equal. The relation between these things are equal, we can say. So let's to prove, we want to prove that there is an equivalence relationship between these two things. So let's say A mod 10 mod 3. So this is the relationship we want to prove. So at the first thing we have the reflexive part. And what is reflexive? In the two way we have the same thing. So what is this? This is for proving the equality between them. So we have just to write this thing. 10 mod 3 again. Okay. So the results are going to be same. No matter in whichever way we write, the results are going to be same, and it is going to be 1 equal 1 for the two places. Now, there says that there is an x and there is an y. Okay, so 10 mod 3, we said that two, two equivalence relationship is what we said. It said that equivalence relationship is where it will be capturing the equality of any binary relationship. It's a special type of binary relationship where two objects are being equal. Equivalence relationship shows that two objects are equal. It's a special kind of binary relation. It's a special kind of binary relation. So if I say that we have another thing as y, this one is y, and we are trying to prove the symmetric relationship where if we have two parts like x and y, two parts, relationship between x and y is equal. We want to prove that, and we are trying to prove the equality of this thing. So let's say how we can prove this equality. We have to also symmetricness. If we write the second thing in the first place, what will happen? If we write the second thing in the first place, that means 7 mod 3 is equal to 10 mod 3. These two are the same things, because no matter if you write the second one in the second place or in the first place, it is going to give you the same output, and the values are going to be same, 1 and 1. The values are going to be same, the values are going to be same, and it is going to be 1 equal 1. So with this function, it is proof the symmetricness. Now there is another thing, that if I write 7 mod 3 or say 10 mod, this one I have written. So I have to introduce one more thing, and I have 13, sorry, 7 mod 3 equal 13 mod 3. So it means that 10 mod 3 is equal to 13 mod 3. That is the transitive relationship between this binary function. So in this binary function, as you can see, that we are trying to find out the values which are going to give us the 1. So it will be, the function will be, this binary relationship will be equivalent relation if some features show equality. And we can see that there can be many values in that part, but it is showing equivalence for this particular range of values. It says that this relationship, binary relationship, is equivalent if those two shows some equality in some feature, not all the things, in some feature. Okay, so this is an example of the equivalence relationship. So this is the end also of the function part. Is there any problem?
Ma'am, are you here?
I cannot understand. Is there any problem?
Ma'am, transitive relationship at 10 mod 3 is equal 7 mod 3 and 7 mod 3 is equal 13. এটা যদি আর একটু ক্লিয়ার করতেন।
Yes, as you say, as you have seen in the transitive part where we have showed this thing. How is it? You can see in the first one we have to take the same things in the two sides from of the equal relationship. Okay, and the next one we have x in the form of x x relation with y and y with x. This is the second part we have to prove, isn't it? That one side of the relationship there will be x which is 10 mod 3 and y is 7 mod 3. We are proving symmetricness of this relationship, and 7 mod 3 equal to 10 mod 3. If these two are going to give us the same values, then we are saying that it is proving the symmetric part. Now transitive part says there are going to be three different values. And if we say that x is equal to y, and we also say that y is equal to z, the relationship which is equivalence, so x is equal to y and y is equal to z, then it will imply that x is equal to z. That is the transitiveness. And if the transitiveness is true, that means they are equivalent. So we have 10 mod 3 and 7 mod 3. 7 mod 3, this were equal, and 7 mod 3 equal to 13 mod 3. Okay, so if this is, let me write this thing. If this is x and we are going to write equal to y, 7 mod 3 is equal to y, and 7 mod 3 being y is equal to 13 mod 3 which is z. Now it will imply that, as we can also see, it is implying that 10 mod 3 is equal to 13 mod 3, which proves that y x is equal to z. Okay, which also shows that x is equal to z according to this format, where x is 10 mod 3 and y is 7 mod 3, and again 7 mod 3 by equal to 13 mod 3, these two are equal, so x is equal to z. Okay, this proves
Yes,
the
ma'am.
transitiveness, and we can say that this relationship is one equivalence relationship. Now clear?
Yes, ma'am.
Okay, next thing we have is graphs. Next thing we have are graphs. So graph is very easy for me. Have you done any course for graph
Yes, ma'am. Statistics.
or discrete mathematics, right?
Yes, ma'am.
In
Statistics.
discrete, ma'am.
But when I was in our course curriculum in my honors life, there was graph theory, a different course. Graph theory was a complete different course, but it's an easy one. Let me tell you. So graph is also going to be needed in this course later for any implementation. So we know that graph. What is graph? What is our idea about graph?
Graphical representation.
It is just some points connected with some lines, right? Graph is just some points connected with some lines. Okay. So these points are called nodes and or vertices. The points we can see.
Once again,
Yes, graph is a set of points which are connected with some lines. Graph is a set of points which are connected with some lines. Okay. So now we can see there are several examples of graph here. 1, 2, 3, 4, 5. As you can see, their numbers are written, and these points are known as vertices or nodes. These points are known as vertices or nodes. Okay. Now the lines, connecting lines, which is connecting from one node to another, is known as edges. The connecting lines known as edges. So there are the terms written here. Graph is something where there is some points, they are connected with some lines. These points are known as nodes or vertices. Maybe this is familiar to you, but let me write this thing again. Singular term is vertex. Singular term is vertex. So the points are known as nodes or vertices, and the connecting lines are known as edges. What is degree? The number of edges coming or going, the number of edges in a node. The number of edges in a node is known as degree. So tell me, what is the degree of 1? What is the degree of 1 in the picture A? Degree says that the number of edges coming from any vertex or
5
any.
and 2.
Ma'am, 2 degree.
Ma'am, 2, because there are two nodes.
1 is 2. And what is the degree of 1 here?
3, ma'am.
3.
It's 3. And here it is 4, right? Okay, it has different, one has different values in this one. Okay, like this one has 4, this one has 3, and this one has 5, isn't it?
Yes, ma'am.
Yes, ma'am.
Each one of them has separate value. Okay. Now there is one more thing, that is loop or self loop. What is this self loop? If one edge comes out of one node and finishes at that node. On that node, the main term here is the edge will be starting on that node and will be finishing at that node. Why am I saying this edge? Because as you can see that if I start from 1 and I travel to 2, 3, 4, 5, again I can finish at 1. But this is not a self loop.
हाँ बोलो.
Any problem?
তারপরে পরে বল দে.
Please mute yourself.
ম্যাম সেলফ লুপটা একটু আবার.
Okay. Self loop is when one edge will be starting from one node and will be finishing at that node. You have seen self node. Okay, self loop. It will be like it is starting from C. One edge is starting from C and finishing at that tree also. That means one edge is starting at one node and finishing at that node also. That is known as self loop. Okay, so the main point here is there is an edge which is going to start at one node and finish at the same node. Like in the edges that are here, that starts at one node and finishes at some other node. But for self loop, the edge will be starting at the starting and end node will be same for self loop. Okay.
Okay, ma'am. Okay, ma'am.
Okay. So we can say that this is a graph G. This is a graph G where the number of vertices are represented using V and number of edges are represented using E. So graph G is a set of vertices and edges V and E. So how we can represent this thing in the form of set? This is the form of set we have here. You can see here that G is the graph with number of vertices here 1, 2, 3, 4, 5. This one for the one for the graph A, where we have the number of vertices 1, 2, 3, 4, 5. Okay, so 1, 2, 3, 4, 5 are the vertices here, and we can represent the edges. How can we represent the edges? The edges can be represented in the form we have used for Cartesian product. You can see 1 and 2 is 1 8, 2 and 3 is another 8, 3 4 is another 8, 4 5 and 5 1 are another edges. So these are all the edges we have in the graph. So graph G will be represented in terms of the vertices and in terms of the edges. In terms of vertices and in terms of edges, so the number of vertices are 5 for the graph A and the number of edges are 6, and these 6 edges are represented using this format where there is an edge between 1 to 2, there is an edge between 2, 3 and all these things are represented here. Now tell me what will be the graph representation in terms of V and E here. In terms of vertex and edge represent the graph B. Can you do this?
Yes, ma'am. 1, 2, 3, 4 will be the vertex, and the edge will be 1, 2, 2, 4, 4, 3, 3, 1, 1, 4, and 3, 2.
Okay. So there are 4 vertices and there are edges. How many edges? There are 6 edges. 1, 2, 2, 4, 4, 3, 3, 1, and 1, 4. And you can see 2, 4 or 2, 2, 3 or 3, 2. Any one of them. Right? Now there is one more thing. Okay.
Ma'am, is there any self loop, ma'am?
So there is no self
Self
loop
loop, yes.
in this one.
Ma'am, self loop is start and end with the same verticals.
The definition here from it clearly. Self loop is for an edge. For an edge, the starting and ending node is same. For a particular edge, the thing here to be concentrating is the starting and end node for a particular edge is same. Why am I mentioning that the starting and end node? Why it is not important to just mention the starting and end node?
Ma'am,
Yes.
your voice is too low. We cannot hear properly, ma'am.
Okay. So I am going to be a bit louder again. So the thing is, starting and end node of a particular edge. Starting and end node of a particular edge should be same. Why am I saying this? I say to you, if I just say that there will be a self loop if the start and end node is same. How it is not going, it is going to be an ambiguous definition. Say that if I start from 1 for this start symbol, I can, the start and end node will be same if I travel to 1, 2, 3, 4 and 5 and then come to 1. But it is not self loop. It is not self loop. For that definition, why it is important to mention one edge is self loop is represented with only one edge. So one edge, say one edge is coming out of here and just coming back here. So if I want to use some symbols here, mm, so not working. Okay, this is not being carved.
Ma'am, you can use Chrome Canvas. That will be better, I think.
What should I use?
Ma'am, Chrome Canvas. In the Google Chrome, there you will be find one option for the canvas. You can draw there.
Okay, it will take time, I think, to find that and to load that also. If we try this thing again, there is no,
Ma'am, you can draw in paint.
again that will take time.
Ma'am, today class time is nearly enough.
We understand now the ma'am self-loop, ma'am.
So do you understand the self-loop?
Yes,
You
ma'am.
are causing some questions, that's why I am trying to show this. I don't know, so it is not there, as you can see. Okay, I'll try to show you it in the next class. I hope you understand all the things here. Okay, then see you in the next class. Have you given your
Yes,
attendance?
Yes, ma'am.
Yes, ma'am.
Okay, then you may leave.
Ma'am, you are supposed